Welcome to this video about spacetime and spacetime diagrams, part of the general relativity section of the astrophysics part of advanced higher physics. Let's have a look at the things that we're going to be learning today. So we're going to be considering spacetime and learning what it is, a three-dimension representation of space and one dimension of time. We'll be linking that to general relativity and the fact that mass will curve space-time, and so gravity occurs because of the curvature of space-time. And we'll be looking at the fact that light will follow a shortest path between 2 points, a geodesic within space-time. And we'll be looking at space-time diagrams and the world lines for objects which are stationary, move at constant velocity, or accelerate. So, what is space-time? Well, according to Einstein, he considers that space and time aren't separate, they're linked together. So we have the three dimensions of space, x, y, z, and we have that dimension of time. And he said the universe exists in these four dimensions called space-time. The diagram at the bottom, the squares on there are representing the space-time. And we can see that the mass of the Earth is distorting the space-time. So he was able to describe and explain gravity and the forces between objects in terms of this 3D curvature of space-time, as opposed to Newton's classical models of forces between two masses. And in fact, he was able to do better than the Newtonian models and predict things that the Newtonian models were unable to explain properly. So, curvature of space-time. So one of the analogies we often use is that of a rubber sheet, like a trampoline, and that mass can stretch the space-time. We can see on this picture here that this sheet has been stretched over this rim, much in the same way that you would do over a trampoline rim, and there is a mass that is in the center of it, and this mass is representing the mass of a planet which stretches the space-time around it. And you can throw balls across and round, and the path that the ball will follow depends on the curvature of the space-time. And we'll share this video with you later on. So here's a similar picture from a slightly different point of view, showing out that the white object is orbiting around the object. It's probably going to get closer and it's going to end up crashing into the planetary mass in the middle there, but it's doing that because the space-time itself is stretched and distorted. So Einstein said gravity is not a force, it's the bending of this space-time. And objects move and accelerate according to the shape of the curved space. Newton's first law says objects will continue to move at a constant speed in a straight line or at a constant velocity. The curvature of space-time means that we see planets moving in circular orbits when in fact they're moving in straight lines, and it's the space-time itself that is curved. So what are we meaning by that? Well, let's have a look at a journey from London to Los Angeles, or even San Francisco. And so this might be the flight path that the plane would take from these two places. But the map on the left there isn't considering that the Earth is spherical. So it looks like it's following a curved line, but actually it's a straight line on the 3D map. So if we're following that path, we're actually following a straight line on the curve. And the shortest distance between 2 points on that curve is called a geodesic. So it looks curved to the one on the left, but if we put that same line on there, we could get a straight line around that curve, this geodesic. So space-time diagrams. So here's one particular representation of a space-time diagram. So as we've said, it has the 3 dimensions, x, y, and z, and also has the combination of time. And Einstein used these to help visualize the motion of objects through space-time. So 1 or 2 of the space dimensions is shown on the x-axis. Okay, so we don't show all 3 because it's too complicated to show that. And on the y-axis we show time. So that is different to a normal distance time graph where our distance is normally on the y-axis and our time on the x-axis. Within our space-time diagram we can have what we call a world line of how things are and when things move. So let's have a look at that. So imagine we're looking at, there's this boy and there's the man on the Zimmer frame and they are moving. So at the beginning they both start at point 0. No position on the x-axis and the time on the y-axis. The boy takes 5 seconds to go 15 meters and ends up at this point on the right here. The man is much slower on his Zimmer frame. After 5 seconds, he's only gone 5 meters. After 10 seconds, he's gone 10 meters. After 15 seconds, he eventually gets to the end because he's going much slower. The boy stays at the finish line waiting for the man, and that's why we see 3 pictures of him. So after 10 seconds, he's still waiting. At 15 seconds, him and the man are there. So the orange line is the world line for the boy. This describes the motion that the boy took. The blue line is the world line for the old man. And this is a space-time diagram because the x-axis is the space and the y-axis is the time. Okay, so the world line is a line on a space-time diagram that shows the motion of an object through 1 or 2 dimensions of space and through time. Constant velocity is a straight line. A curve will represent acceleration. So in this diagram here, the old man had gone 5 after 5 seconds, had gone 10 after 10 seconds, and 15 after 15 seconds. That is producing that straight blue line because they're moving with a constant velocity. So the x-axis often has units of light years, and the y-axis can have units of years, and then the speed of light can be shown on a space-time diagram. We'll see that a little bit more in a moment. And it's like our displacement time graph, but it's different because time is on the y-axis and the position in space is on the x-axis. So if we look back to our cone example we had earlier, we've got our y and our x-axis there, and we've got our time. So above point E, we've got our future time. Below point E, we've got our past time moving down the page there. The world line of some observer could be that squiggly red line in the middle there. Now, why have we got a cone? We've got a cone because nothing can go faster than the speed of light. So there's only certain parts of the diagram that objects can be moving within. you can't go faster than the speed of light, so you can't be in the area that is an angle greater than 45 degrees from the y-axis, because to do so would require you to move faster than the speed of light, which we know is not possible. So you have these cone shapes, these places where you could possibly be within the future or within the past. Okay, in reality, that's actually 4-dimensional, 3 for space and 1 for time, but that's much harder to visualize, so we simplify it to show time and either the 2 dimensions that we showed there or the 1 dimension from there. So here's a diagram with just the 1 dimension, the x, and the time. So this is representing the same motion that we saw with the diagram before, except because it's a flat image, we're not seeing the cone shape. But we can only be within this particular section with the angle being less than 45 degrees between the time and the world line, because the world line for light is at 45 degrees and we can't get faster than that. So we can't occupy those spaces. So what have we talked about there? So we said different regions of the space-time diagrams have different significance. The diagonal lines correspond to a speed equal to the speed of light in a vacuum, which we call c. The regions within the diagonals are where the speed is less than the speed of light, c. The regions outside the diagonals cannot affect or be affected by the event, since messages cannot travel faster than the speed of light. So there can be nothing going on outside those 45-degree lines. The present corresponds to where the time is 0, and the future the time's increasing, and the past the time's decreasing. So the bit below the x-axis is the past. A particle's position at an instant in time is called its world line. Each point of the world line is an event that can be labeled with a time and a position in space. Let's have a look at some world lines. So let's say you're sitting on your chair in your room, you're not moving. What would your space-time diagram look like? Well, you're not moving through space, you are moving through time, so we have a vertical line here because there's no moving on the space axis because you're not changing your position. So an object moving at a constant speed could be shown by either of these space-time diagrams, where the world line could start at 0 or the world line could start at any position in space, because the position in space is relative to another one. And because they're moving at constant speed, that line needs to be straight. Remember, the greater the gradient of the world line, the less the velocity. This is because we're looking at time on the y-axis and space on the x-axis. So usually our displacement time graphs are the other way round, which means that the greater the gradient, the greater the velocity. So here, large gradient means slower, small gradient means faster object. So you can say the blue object is moving at a constant velocity, but it is a greater constant velocity than the orange one or the red object. Where an object is accelerating, then the space-time diagrams are going to have world lines of changing gradients. So curved lines on space-time diagrams indicate accelerating or non-inertial frames of reference. And if you consider the graph, you can work out whether it's going to be an accelerating or a positive acceleration, or a decelerating or a negative acceleration by looking at the gradient and how it's changing. Remember, this is the opposite to normal because we've got the time on the y-axis. So an increasing gradient means a decreasing rate of velocity, so a deceleration. Okay, we can get simultaneous events, ones that occur at the same time, and these can be shown as a flat line. So they're moving through space, but they're happening at the same time. Okay, so here's our summary of our world lines. A straight line for a stationary object, vertically. Curved lines for accelerating objects. And straight diagonal lines for constant speed, with greater gradients being a lower speed, lower constant speed than the other ones. Okay, so we should have an awareness of what space-time is, the three dimensions of space, x, y, and z, and time, and we should have an awareness of what general relativity is and its contribution to curving space-time, and that gravity curves space. And so gravity arises from the curvature of the space. And also that light and other objects moving freely will follow this straight path between 2 points, this geodesic. And we can draw a world line for objects which are stationary, move at a constant velocity, and accelerate.